Assalamualaikum warahmatullahi wabarakatuh to our Dr. Sila. Today, as you can see on the screen, our topics today is system analysis for turbine flowmeter in the industry. And the background is a turbine flowmeter is a device that is commonly used in the industrial sector to measure the flow rate of various fluids such as liquid and gases. It works on the principle of fluid flowing through a turbine rotor, which the spins at a rate proportionate to the velocity of the fluid. A detailed explanation of the working principle of a turbine flowmeter in the industry. First is turbine rotor. The turbine is the height of the turbine flowmeter. This rotor is often composed a lightweight, durable material such as stainless steel and has blades or vanes that mimic wind turbine blades within the fluid carrying pipeline. The rotor is housed within a flow tube. And the second is the fluid flow. The fluid tube allows fluid, liquid or gas to impact on the turbine rotor blade. The fluid force lead a rotor to begin rotating. The rotating speed of the rotor is proportional to the velocity of the fluid flowing through the flowmeter. And it's more detail in the working principles such as a sensor and pickup, signal processing, calibration, and the display and output. And the second main point is suggest one application of the instrument device. From the question, we can answer is in the aviation sector, turbine flowmeters are commonly used to measure fuel usage. Turbine flowmeters are used in aviation fuel system to properly monitor the flow rate of jet fuel as it is supplied to the engines. These parameters is critical for flight operation, safety and effective fuel management. In aviation, precise fuel flow measurement are essential for various reasons. The first point is fuel efficiency. Fuel consumption monitoring aids in optimizing fuel usage, ensuring that the aircraft function efficiently and minimizing fuel waste. This is critical for lowering operational costs and decreasing environmental impact. And the second is flight planning. Accurate fuel flow data is flight crew en route planning and decision making on in flight diversion or alternate landing places based on fuel availability. And third is safety. Maintaining adequate fuel level is critical for flying safety. Turbine flowmeter help to avoid situation in which fluids run critically low, ensuring that the aircraft also has enough fuel reserve. And maintenance. Monitoring fuel flow can also provide information of the engine performance and of an aeroplane. Deviation from plane fuel consumption rate may indicate engine problem that need to be addressed. And five, compliance. Airlines and aviation authorities often require accurate record of fuel consumption for regulatory compliance and adulting purpose. And this YouTube video link for explanation. And then this is a sketch and label schematic diagram of overall process. And we proceed to advantage of turbine flowmeter. Turbine flowmeter provide a number of advantages in industrial application which contribute to their popularity and widespread adoption. Among the many benefits of turbine flowmeter are: first, higher accuracy. Turbine flowmeter are known for their great precision, making them ideal for application requiring accurate flow measurement. Even at low flow rate, they can offer reliable readings. And second is wide flow range. These flow meters can measure a wide range of flow rates, from slow to fast, making them useful for a variety of industrial processes. The third, quick response time. Turbine flowmeter respond quickly, allowing them to offer real-time data on changing flow rates, which is critical for process management and monitoring. Fourth is linear output. Turbine flowmeters typically generate a linear output signal, such as frequency or voltage, that is proportional to the flow rate. This linearity facilitates data interpretation and calibration. Fifth is compact design. They have a compact and space-efficient design, making them suitable for installation where space is limited. And last, from my side, is versatility. Turbine flowmeters can measure a wide range of fluid, including liquid and gases, as long as they are clean and not viscous. Because of their adaptability, they may use in a variety of industries.
Alright, so good afternoon to Dr. Sila and also everybody. This is part B, which is system analysis for turbine flowmeter in the industry. So I'm going to start with advantage number 7, which is reliability. So turbine flowmeters are noted for their long-term dependability and durability when properly maintained, which means they are resistant to wear and tear and can survive tough operating conditions. And then we have low pressure drop. So turbine flowmeters typically introduce minimum pressure drop in the fluid system, which is beneficial when dealing with pressure sensitive systems. And then we have digital and analog outputs. So they can provide both digital and analog output signals, making them compatible with various data acquisition and control systems. And then we have ease of installation, which means they are very easy to install and also require very less pipe modification. And then we have remote monitoring, which means many turbine flowmeters include remote monitoring, allowing operators to track flow rates and performance from a distance, which is very valuable in large-scale industrial installations. And then you have low maintenance, which means like turbine flowmeters require low maintenance and which with periodic cleaning and calibration. And then we have cost-effective. So turbine flowmeters are very cost-effective and require very low purchase price and also have long-term dependability. So turbine flowmeters, although turbine flowmeters have numerous benefits, it's vital to remember that their usefulness for a given application depends on things like the fluid type, the flow rate range, and the ambient circumstances. In order to guarantee accurate and dependable flow measurement in industrial processes, proper selection and installation and maintenance are very, very essential. So next I'm going to talk about the limitations of turbine flowmeter. Turbine flowmeters are widely used in industrial applications due to their many advantages, but they also have certain limitations and considerations that should be taken into account when selecting and using them. The first one is fluid compatibility. So The finest fluids for turbine flow meters to use are clear fluids, free of solid particles or abrasives. The rotor can be harmed by particulate matter or contaminants in the fluid, which can also reduce precision. Other flow meter types such as magnetic or ultrasonic flow meters might be more suitable for these applications. Number 2, we have viscosity sensitivity. High viscosity fluids, which is fluids having a thicker consistency, may create incorrect readings from turbine flow meters because higher resistance can make the rotor rotate more slowly. Although less common, specialized turbine flow meters for high viscosity fluids are available. And then we have limited turndown ratio. The range of flow rates that a flow meter can precisely measure is indicated by its turndown ratio. Turbine flow meters typically have a restricted turndown ratio and flow rates outside of their designated range. Their accuracy may considerably also decline. Number 4, we have pressure and temperature limitations. So, fluid pressure and temperature variations might affect how sensitive a turbine flow meter is. The density of the fluid can vary depending on various factors, which can alter the accuracy of the flow measurement. There may be restrictions on the highest pressure and temperature that some turbine flow meters can withstand. Number 5, we have maintenance requirements. Turbine flow meters are very low maintenance equipment, but they do need very high cleaning and calibrations to stay accurate. If ignored, they might cause the performance to decline. Number 6, we have flow profile sensitivity. So turbine flow meters might give up incorrect readings because they are susceptible to flow profile anomalies like turbulence and swirl. The flow profile can be stabilized by installing straight pipes. Number 7, we have limited low flow rates. So just because the rotor professional speed drops to a very low level, turbine flow meters might not be appropriate for applications requiring very low rates. This is because it becomes challenging to take measurements. Number 8, we have mechanical wear. The turbine flow meter's rotor and bearings may degrade mechanically over time, which could have an impact on long-term accuracy. To minimize it, proper maintenance is very important. Number 9, we have fluid density variations. So change in fluid density due to variations in composition can affect the accuracy of the turbine flow meters. Some applications may require compensation for density changes. Number 10, we have risk of cavitation. So cavitation can happen in situations where fluid pressure drops quickly, such as high pressure to low pressure transitions, which could harm the rotor and affect measurement accuracy. Explosive or hazardous environments as the last one. So turbine flow meters may not be suitable for use in explosives or hazardous environments unless they are designed and certified for its conditions. So when selecting a flow measurement solution, it's critical to carefully consider these limits and evaluate the unique requirements of your application. Alternative flow meter technologies might be more appropriate in situations where turbine flow meter constraints are problematic. So the last thing in part B is to discuss predictive maintenance planning, including calibration planning for the overall system. So for a turbine flow meter system, predictive maintenance planning, which includes calibration planning, is essential to guarantee accurate and reliable measurements, save downtime, and also increase equipment lifespan. Here is an example of how the total system of turbine flow meter might benefit from predictive maintenance and calibration planning. So what we have to do is, number 1, data collection and sensor monitoring. So the turbine flow meter and its connected sensors must first continuously gather data on flow rate, temperature, pressure, and also other any pertinent variables. To make sure that the sensors are operating properly and delivering accurate measurements, they must be periodically checked. That entails looking for any indications of drift or departure from anticipated values. Number 2, what we have to do is data analysis and predictive maintenance. Utilize cutting-edge approaches to analyze the gathered data in order to find patterns, anomalies, and trends that might point to potential problems with the turbine flow meter's operation. And then we should create predictive maintenance algorithms that can forecast when maintenance is necessary by taking into consideration previous data, operating circumstances, and also performing thresholds. And then we should set up alerts or messages for when the analysis identifies anomalies that might call for calibration or maintenance. The step number 3 is calibration planning. Make a schedule for calibrating the turbine flow meter and the connected sensors. Manufacturer instructions, industry norms, and the importance of the measurements should all be taken into consideration when determining the calibration frequency. So to guarantee that the flow meter and sensors are calibrated accurately, choose the proper calibration tools and procedures. Technicians with the appropriate training or approved calibration services should carry out calibration. And then you must ensure that you keep through records of calibration activities, including the date of calibration, the outcomes, revisions, and also the next anticipated calibration date. This is very important so that you could go back and check. Number 4 is integration of calibration and predictive maintenance. So utilize calibration data in the process of preventive maintenance. Examine calibration records for strengths or variations that might point to the need for flow meter maintenance or alterations. Establish calibration thresholds that if reached will cause maintenance or calibration actions. An alarm for preventive maintenance might be sent, for instance, if a sensor calibration goes out of predetermined limits. Number 5, we have work order generation and scheduling. A work order containing information about the individual maintenance activities, including calibration necessary, should be generated when the predictive maintenance algorithm indicates that the maintenance or calibration is required. These jobs should be scheduled by maintenance teams depending on their importance, the resources that are available, and the urgency of the anticipated maintenance or calibration needs. So, number 6, we have remote monitoring and reporting. Implement remote monitoring capabilities that allow operators to track the turbine flow meters performance and sensor health in real time. Then we should generate regular reports summarizing the turbine's operational status, calibration history, and any predictive maintenance actions taken. Number 7 is cost optimization and efficiency. Integration of calibration and predictive maintenance helps optimize maintenance costs by ensuring that the calibration and maintenance activities are performed by only when needed, minimizing downtime and reducing unnecessary expenses. Then we have continuous improvement as last one. So we should use feedback from calibration and maintenance activities to fine-tune predictive maintenance algorithms and improve the accuracy of precision over time. This is why important is because you can use the old records to go back and to check which is your mistake, and you could not make the mistake again and be always a step forward. So in summary, predictive maintenance planning for a turbine flow meter system, including calibration planning, involves continuous data collection, analysis, and proactive scheduling of maintenance and calibration activities. This approach helps ensure accurate measurements, prevent unexpected failures, and maximize the efficiency and reliability of the flow measurement system. That's all from me.